First talk after the Lunar New Year. So today is our great pleasure to have our speaker Robert Nicklas speaking with us from Boston College. So Dr. Nicklas got his PhD at the University of Maryland, but he has a lot of collaboration. Has shown the different logos that listed here on the cover page. So Robert has been focused on the mantle redox in the recent couple of years, and he's going to present his research on the topic in today's talk. So for this online webinar, normally we run for 40 minutes of talk, but it's very flexible. And then we have about 15, 20 minutes of interaction with our participants.
Okay.
So as we agreed before, so this talk will be recorded and posted on YouTube for outreach. So here it is. Robert, welcome.
Thank you. Thank you for that introduction, and thank you for inviting me. So as they said, I'm Robert Nicklas. I go by Willie, but you can call me Robert. You can call me Willie. I don't care. And I'm here to talk to you for my talk, Redox Heterogeneity in the Terrestrial Mantle, from the Archean to Modern Plume Lavas, which will kind of step through. I've been working on redox since 2014, almost 10 years now of terrestrial lavas. And we'll start with some of my work for my PhD at University of Maryland, then my first postdoc at Scripps Institution of Oceanography at UCSD, and my current work that I'm still working on at Boston College. So just some collaborators and funding, some PhD collaborators, some postdoctoral collaborators, and all of this has been NSF funded or funded by funds from Boston College. So I'll talk quite a bit about FO2, or oxygen fugacity in the mantle. And for many of you that aren't petrologists, it's good to sort of define that term because it's kind of a nebulous term. So oxygen fugacity is an intensive variable in petrology. It controls the behavior of redox-sensitive elements. The number one redox-sensitive element is iron, but lots of important elements have different valence states at different oxygen fugacities within sort of terrestrial igneous systems. They include vanadium, chromium, molybdenum, many more, and also things such as hydrogen, sulfur, carbon, which are important because they degas. And different degassing processes are very strongly dependent on oxygen fugacity. So FO2 is probably best understood as the amount of molecular oxygen. Bear in mind, molecular oxygen, not oxygen bound in silicate tetrahedra, in an igneous system at equilibrium, if that system is at equilibrium. Like all equilibria, it depends on temperature and pressure. So we normally report oxygen fugacity as relative to a mineral redox buffer. This is just from a sort of review of Lindsley, 1991. Here is a bunch of different redox buffers that are commonly used. The two we'll use in this talk are NNO, nickel oxide, and FMQ. FMQ is phaelite magnetite quartz, which is written out down here, phaelite magnetite quartz, and nickel oxide. It's generally been shown, with some caveats, that the FO2, or oxygen fugacity of igneous rocks, is a proxy for mantle FO2, and that unfractionated lavas, i.e. lavas that haven't evolved via AFC processes, closely resemble their mantle sources. So we can sort of probe the FO2 of mantle reservoirs by looking at the FO2 of mantle-derived lavas. So this is a figure from Lee Kump from 2001. And this is obviously greatly simplified, but I really like this figure because I think it kind of illustrates a lot of what I'm interested in with my research. It's obviously not to scale. The crust is not this big. So what we have here is, in this very simplified diagram, we have an oxidized crust. We know we have an oxidized crust because we have 23% oxygen in our atmosphere. And that leads to very oxidized mineral species. And the upper crust and sediments are very oxidized. And for instance, altered oceanic crust has an iron +3 over total iron ratio of up to 0.5, 50% of the iron is oxidized. The mantle is much more reduced, and it has maybe 2 to 6% of its iron is oxidized, so that the surface and the deep earth are out of redox equilibrium with each other. However, there are some processes where the reduced mantle and the oxidized surface interact with each other. There's mid-ocean ridge volcanism, where we get reduced species coming out of the mantle to form morb. There's subduction and delamination of both sediments and oceanic crust, and also perhaps lower continental crust, in which we recycle oxidants into the mantle. There's also plume volcanism, where we might be returning some reduced material and some oxidized material up in plume lavas. This also shows a quote unquote primordial sort of oxidation state in the lower mantle that might be different than the ambient convecting mantle, but we'll talk more about that. So this is a very good figure, and I think summarizes the sort of central point of redox in igneous systems on our planet pretty well. But a lot of what my research throughout my short career so far is looking to see if we can get a finer scale picture of mantle redox and whether this green region can be more closely defined than simply all being the same. So part one, we're going to talk about mantle oxidation from the Archean to the present day. We'll talk about temporal heterogeneity in the mantle. So first off, I'm going to define komatiites because I've worked quite a bit on komatiites, but komatiites are very unusual and most people have not worked on them. So we'll go through this a little bit. Komatiites are mantle lavas. They're the hottest lavas erupted in geologic history. Some of them have liquidus temperatures as high as 1800 Celsius. They're very, very hot. They're high degree partial melts, up to 50% partial melting in some cases. They differentiate extensively in situ once erupted. This is from the Alexo region in Canada. This is kind of the archetypal beautiful komatiite flow, where komatiites have very, very low viscosity, so they fractionally crystallize sort of very, very strongly, and only olivine. So you'll get a chilled upper margin, you'll get a spinifex layer. This is all olivine. Olivine has a very strange crystal habit that looks like grass almost when it's at very high temperatures. And then you'll have an olivine cumulates. So these komatiites are only, with one notable exception, known to erupt in the Archean. They're thought to be from a hotter Earth. We had a higher mantle potential temperature. We get plume lavas that are considerably hotter than plume lavas today. And they have been used extensively to constrain mantle evolution. And we use them throughout my PhD research to constrain mantle redox evolution. We looked at an extensive set of komatiites from around the world and constrained their oxygen fugacity to get to the oxygen fugacity of the plume source mantle throughout the Archean. So why did we do this? So for many of you, and especially people who do low temperature geochemistry, we were interested in the great oxidation event, which I'll refer to as the GOE from now on. So basically what the GOE is at the Archean Proterozoic boundary at 2.4 billion years ago, oxygen irreversibly rose in the atmosphere from less than 10 to the minus 5 atmospheres to around 1% of what we see today in the Proterozoic, as you see in this figure down here. It's become increasingly clear that oxidative photosynthesis is evolved 300 to 500 million years prior to this. So this was not a biological innovation alone. A biological innovation was required, but it was not only a biological innovation. Some other O2 source or sink changed rather dramatically. We reached a tipping point around 2.4 billion years ago. There's a wide variety of theories for what caused this. It includes rising of felsic crust. Felsic crust is less good of an oxygen sink than mafic crust. Rise of subaerial volcanism, same idea. Subaerial volcanism is less good at removing oxygen than submarine volcanism, or a single large igneous province. So basically what we're doing here is we're looking to see if the deep Earth also shows a redox evolutionary trend to match that of the atmosphere at the time. And we're using komatiites to do that. And why we think that might be true, why we think the deep Earth and the atmosphere might show sort of matching redox trends, excuse me, is it's been theorized by Jim Casting in 1993 and then by Dick Holland in 2002 that mantle and atmospheric redox are coupled, even though the mantle and the atmosphere do not have the same oxygen fugacity. The mantle oxygen fugacity exerts a strong control on the evolution of the atmospheric oxygen fugacity. Why does this happen? Reduced volcanic gases are a major, to this day, oxygen sink. Each eruption removes quite a bit of oxygen from the atmosphere, and changes in mantle FO2 change the magnitude of the oxygen sink. So essentially, if the mantle gets more oxidized, then subaerial and submarine volcanic gases become less efficient at removing oxygen from the atmosphere. And therefore, an increase in mantle FO2 can lead to the rise of atmospheric oxygen. Previous literature have examined this idea, most notably Keneal 1997 and Lee 2004, found not more than 1 to 2 log units of change in mantle FO2 since 3.5 GA. But we wanted to look sort of finer scale at this. So we took sample localities from many, many places around the world. And I'm always looking for more komatiites. Like, this project's done, but I would do it again tomorrow to look at more komatiite FO2. The problem is we need komatiites that preserve magmatic minerals, and finding magmatic minerals in the Archean, for anyone that's worked in Archean terrains, is really not trivial. It's very, very difficult. It's overall very hard to find things that still have like olivine in them after billions of years, but we found a bunch of them. We found several of them in Zimbabwe, in Kapval, Spirit Kraton. My former advisor, Igor Puktil, is sort of known for work in the Baltic Craton. So like we had a lot of Baltic lavas. And also some piccrites from Songda in Vietnam, and from, this is supposed to be Hawaii, but Hawaii is not on this map, and Iceland, and the one place in the world that komatiites that are Phanerozoic erupt, which is in Gorgona Island in Colombia. So we did quite a bit of fieldwork. This is not my fieldwork, Skapenberg, but Kumo, Finland, and Gorgona Island, Colombia are both my fieldwork. And we went out and we sort of extensively sampled these komatiite flows in sort of different localities and tried to find magmatic minerals. It's often a real search when you look in Archean terrains to find rocks that have preserved things for, in some cases, these Skapenberg ones are 3.55 billion, have preserved olivine for billions of years. Given how easily olivine weathers, it's kind of amazing. So I've talked quite a bit about oxygen fugacity, but how are we going to constrain oxygen fugacity? So there's a couple of ways of doing it, but the way I did it, largely because magmatic glass is never preserved in Archean terrains, a lot of sort of ways of measuring FO2 require magmatic glass, kind of fresh volcanic glass. We're not going to get that in the Archean. But what we can get instead is olivine. So what it has been found from experiments, extensively from experiments, is that the partition coefficient of vanadium is a redox sensitive element, into olivine over melt, varies very strongly as a function of FO2. But this is FO2 in log units relative to the nickel-nickel oxide buffer, and this is the partition coefficient of vanadium into olivine. You'll notice that there's a very strong correlation here across many different types of experiments. There's not nearly as strong an effect of either temperature or melt composition. These vertical arrays of data show same oxygen fugacity, different temperature or melt composition. And so therefore, if we can constrain this partition coefficient in a natural lava flow, we can get the FO2 of a sample, kind of back this all out. Why does this work? Basically, unlike iron, which in terrestrial lavas is only +2 or +3, vanadium in lavas varies all the way from +2 to +5. But right here, around QFM -2 to +2, it's varying between 3 and 4 and 5. So essentially, in this region, vanadium goes to higher valence as oxygen fugacity increases, and lower valences of vanadium, namely +2 and +3, are much more strongly compatible in olivine than +4 or +5. Therefore, the partition coefficient goes down as oxygen fugacity goes up. Wang et al. 2019 is the most recent compilation of experiments relating this partition coefficient to oxygen fugacity, and they got this empirical correlation from almost 200 experiments across a wide variety of temperatures, melt, compositions, and such. So for each of our komatiite flows, we did whole rock standard addition, which is more accurate than external calibration to determine vanadium contents in each of the whole rocks across a flow. Then we did laser ablation ICP-MS of preserved olivines in each lava flow. This is the best one we saw. This is the Veterany Belt. This is from Northwest Russia. This is 2.5 billion years old. Look how fresh this rock is. This is incredibly fresh. The olivine in the glass is still totally there. That's the one we did 300 in because we found a very large amount of olivine. Some of the flows didn't preserve as much olivine, so we measured as much as we could, around 60 by laser ablation. We looked at the variation between vanadium and MgO content in the whole rocks, and the linear behavior we found for each of the lavas indicated that olivine was the only fractionating mineral, and therefore we could calculate the emplaced or parental lava vanadium content. We measured the vanadium content of the olivine, so we have vanadium in olivine, vanadium liquid, we have a partition coefficient, we can back out oxygen fugacity. This is an example of this. So basically, all of these are bulk rock data, and this is the average of all the olivine data. So all the olivine data, even if you plotted them separately, would all plot down here for each of 6 flows, right here, the olivine. And we can calculate using iron magnesium systematics what the MgO content of the parental magma is. And therefore, we can get the vanadium content of the parental magma from these lines and the olivine vanadium content from just measuring it. And using all that, we can get oxygen fugacity. So this is kind of our results from komatiites versus Morb and the Zanes Morb average. And so what we see right here, we see a decent degree of scatter. But what was sort of most exciting to us is we see a variation with emplacement age. So our oldest lavas show some scatter, but we go from the lowest lava is around 3.48 billion. We see an increasing trend to around 1.9 billion around here. And then after that, we don't really see a trend. And it seems like our more modern picritic lavas seem to overlap pretty well with what we think Morb to be. And sort of, this is a Morb average using vanadium and olivine oxyspirometry, which is what we're using here. And then there's the more conventional Zanes method, which you need glass for, which shows a similar average. So there's a couple of observations about this data. It's that the FO2 of the suites correlate not with petrological type or degree of melting, or any really other. We looked at a lot of sort of geochemical parameters here. We don't really see a correlation with anything but age. So this likely reflects source variation. From 3.48 to 1.87 billion years, we define a linear increase in FO2 of around 1.33 plus minus 0.43 log units. All younger suites show FO2 within errors. So what we infer from this is from sort of the Meso-Archean to the Paleoproterozoic, we get sort of the average mantle is oxidizing of give or take 1 log unit. Additionally, our oldest lavas, the 3.55 GA Scapenberg komatiites, are some of geochemically the most unusual lavas on Earth. They show short-lived isotope anomalies. They show elevated FO2. It's these right here. This is the Scapenberg lavas. So all of these show sort of typical mantle-like isotopic anomalies. They don't show isotopes signatures that would be indicate that they're not representative of the bulk mantle. Scapenberg does. Scapenberg shows 142 neodymium, 182 strontium. It shows neodymium and hafnium values that are very unusual. It shows osmium that is very unusual. Everything isotopic in Scapenberg is weird. And its FO2 also differs from the trend. So this might be some sort of spatial heterogeneity and not sort of representative of the bulk mantle. The rest of them seem isotopically more normal. So we need to talk about how we're going to explain this trend, how we're going to explain our mantle oxidation trend. So the first thing we thought about, here's this figure again, I use this figure a lot, is we look at crustal recycling. As I said, the surface and the mantle are out of redox equilibrium. The surface is more oxidized, and therefore, when oxidized material is recycled in subduction zones, then it has the potential to introduce oxidants into the mantle. So there's a couple problems with this. We did some calculations. So we know for a fact that the bulk of the oxidizing power of altered oceanic crust, most of the oxidants from the surface, are lost to arc lavas. How do we know this? Arc lavas are more oxidized than any other lavas on Earth. Arc lavas show oxygen fugacities up to +3 FMQ, and that's thought to be because of the introduction of oxidants from the subducting slab into the mantle wedge. We do, however, know from mass balance that some of these oxidants do reach the deep mantle, but not all of them. So what we did is we took mass balance, this paper Evans 2012, which I highly recommend, which does a global mass balance of the amount of oxidized species going into subduction zones and the amount of oxidized species coming out arc lavas, kind of does a global average, and shows sort of the amount of oxidants getting pumped into the mantle, mainly iron +3, into the mantle as sort of a mass flux nowadays. So basically, we need to oxidize the mantle by around 1 log unit and around 1.6 billion years. And what if we take the Evans sort of rate of recycling of oxidants, you need a very high recycling rate. It's basically 4 times as much oxidants pumped to the mantle as today to explain the komatiite oxidation trend. This seems highly unlikely. This is a lot more oxidants getting recycled than today. And mind you, this was an anoxic Earth, so altered oceanic crust was not necessarily as oxidized as it was today. We find this model kind of untenable. Basically, the mantle is too big and the crust is too small, that the mass balance does not really work. The second one is this was suggested to me by Bill McDonough, who I used to work with at Maryland, in which he talked about maybe it's coming from the core. And this is much more speculative than the crustal recycling model. So we know a couple things. So the core likely contains dissolved oxygen, and we know from ab initio calculations that dissolved oxygen is incompatible in solid metal compared to liquid metal. So as the solid inner core grows, the liquid outer core will increase in concentration of oxygen. If the outer core were to become supersaturated, it could vent oxygen to the lower mantle, raising its oxygen-iron ratio, and therefore its FO2. It is unknown if atomic oxygen, which is an oxidant, or FeO would escape to the mantle. FeO would not be an oxidant. The really big problem with this is there's no geochemical evidence for core-mantle interaction evident in our sample set, or pretty much any sample set. Core-mantle interaction has never really been shown since core formation. And the other really big problem with this is we know from though I've been told geophysicists have altered their models recently, that thermal modeling shows that the inner core likely began crystallizing at 1.5 billion years, which is too late to explain this trend. We would need an inner core as early as 3.5 billion. So we can safely discount this. We don't think core-mantle interaction explains this, or even that it happens at all. Our third theory, and the one that I've mostly settled on, concerns bulk mantle mixing and heterogeneities left over from core formation. So this requires a little bit of explanation. So similar to how the mantle and the surface are out of redox equilibrium, the mantle and the core, we know, are out of redox equilibrium with one another, because the upper mantle is not in equilibrium with metal. However, we know it was in equilibrium with metal at some point because we have a core and we must have formed a core at some point. So to knock the mantle and the core out of redox equilibrium, mind you, forming a core via equilibrium processes does not do this, because we're still in equilibrium with the core, even if we segregate it. We need some process to knock them out of equilibrium. Sort of the dominant idea among mineral physicists and a lot of people who study like sort of early core formation processes is something called Bridgmanite-driven disproportionation. So Bridgmanite, otherwise known as magnesium perovskite, is the dominant mineral in the lower mantle. It's like 90% of the lower mantle. Bridgmanite highly prefers +3 cations in its mineral structure. So what iron +2 will do in the lower mantle, and this is still happening today, it's been shown in experiments and it's been found in diamond inclusions, is that iron will disproportionate, which means react with itself. So iron +2 will disproportionate into 2 iron +3, which fit really well in the Bridgmanite structure, and also iron metal. This in of itself does not change the oxygen fugacity, because this is a reversible process. However, if we were to lose 1 to 10% of this disproportionated metal to the core, then the mantle would become more oxidized. We would knock them out of redox equilibrium. If we were to lose 1 to 10% of this disproportionated iron metal, and therefore, initially, right after core formation, right after this process, the lower mantle would have a higher oxygen-iron ratio, and therefore we would have to mix the lower and upper mantle. We'd have to sort of mix them well to lead to overall mantle oxidation. So what we postulate is that most of this mixing had occurred by 3.48 billion. Most of the mixing occurred shortly after core formation. However, if this mixing was incomplete, if we still had sort of more mantle heterogeneity left over from core formation in the Archean than we have now, then this could lead to an oxidation trend. If there were still bits of the lower mantle that had not yet mixed with the upper mantle up until 1.87 billion years, the accessible mantle would show an oxidation trend. Mind you, all the lavas we have are from the upper mantle. So when we talk about mantle redox, we're really talking about upper mantle redox. The 3.55 billion year old Scapenborg source is anomalously oxidized, and it shows isotopic evidence for Bridgmanite fractionation at some point in the history of its mantle source, which is consistent with this theory that the lower mantle was more oxidized and also that it contained Bridgmanite at some point. So this kind of supports this theory. What else is supporting this theory is the persistence of short-lived isotope anomalies, 182 tungsten, 142 neodymium, throughout the Archean and throughout Earth history in general, but especially throughout the Archean, that showed that the mantle was not well mixed into the late Archean. So I know that was a lot, so we'll go through some conclusions for part 1, and then we'll get out of the Archean, and we'll keep looking at redox and more modern things. So we have a data set of around 14 komatiites and picrites. And again, if you want to hand me some komatiites, I would happily take them and work on them. We show an overall oxidation trend from Mesoarchean to Paleoproterozoic. FO2 does not correlate with basically anything but time. We show that recycling, the mass balance doesn't work. Core-related oxidation doesn't really work. Late-stage mantle homogenization is currently our best model to lead to the oxidation of the accessible upper mantle. And at the atmospheric rise of O2 in the Great Oxidation Event at 2.4 billion, likely related to this mantle secular oxidation trend. And therefore, this had a strong control on the rise of atmospheric oxygen, the change in mantle oxygen fugacity. So this has been detailed in a whole bunch of papers that are pretty old at this point. 2018, 2019 are the data shown here. And then we did some, in collaboration with David Catling and his postdoc Shintaro Kadoya, we did some atmospheric modeling showing that our oxidation trend could have triggered the great oxidation event. So we're going to move out of the Archean. We're going to continue to look at oxygen fugacity of lavas using the vanadium and olivine method, but we're going to start with some mid-ocean ridge basalt, some morb. So here's a very, very beautiful morb with the glassy rind and then sort of fully crystallized interior. And so what's never really been shown is, up until this point, is I showed you all the komatiite data. And what I was asked quite a bit when I was working on the komatiite data was, how do these compare to modern lavas? Do we have modern analogs for these? While we do have modern high MgO lavas, we didn't really have any sort of morb analogs going back to the Archean. All of the komatiites we looked at were plume lavas. And so what we're doing here is we're looking at morb lavas using our method and more conventional methods for determining FO2 and see if they give the same result. The most conventional method for determining FO2 is called iron Zanes, X-ray absorbance near-edge spectroscopy, which uses volcanic glass and does synchrotron-based spectroscopy on it. And so there's been a global morb average from Cottrell and Kelly 2011 that everyone quotes who works in mantle redox. This is around minus 0.18 plus minus 0.16 delta FMQ. And at the time of when we worked with komatiite data, there was only 4 morbs worldwide that had been analyzed for vanadium and olivine, which is kind of crazy to me. And those gave a similar but different outside of error oxygen fugacity than the Zanes data. So to sort of rectify this, more recently, we acquired a set of morb samples, including morb that was used to define the Zanes average from the Smithsonian in Washington, D.C., and we measured olivine glass pairs, concentration of vanadium in olivine glass pairs, to try to determine their oxygen fugacity and see if we could match our method with the more conventional method. So this is what we saw. Unfortunately, even though we looked at this full data set, they were very nice to lend us all of the sort of glasses used for iron Zanes. Most of them did not contain olivine, only a small subset contained olivine. This was probably intentional on their part because they were looking for clean glass and we were looking for olivine glass pairs. We were kind of looking for different things. But we found olivine in quite a few of them. I believe 12. I'd have to check, 12 or 13. It's been a while since we wrote this paper. And so what we see is the iron Zanes all scatter around the average right below FMQ. The vanadium and olivine data, the ones with more primitive glasses, more high MgO glasses, plot well within the Zanes. You'll notice there's larger error bars on the vanadium and olivine method. There always will be larger error bars. It's not as precise as the Zanes technique, but what's important about it is it can be used in lavas where glass isn't preserved, which is most of the geologic record. However, all of the more evolved morbs show anomalously high oxygen fugacity using our method that does not match the Zanes data. So this is basically most of what I just said. The methods match for primitive morb, and the 4 data that match with primitive morb give an average that overlaps with the Zanes average. So more evolved morbs show more oxidized results. I don't think this is real. I think this is an analytical artifact right here. I don't think their oxygen fugacity is actually close to FMQ plus 1 because that is very high for morb, and it doesn't match the Zanes data, either the Zanes average or the Zanes data for the exact same samples. What I likely think is happening instead is that olivine and glass are not in equilibrium with each other due to either inheritance of clinopyroxene or spinel in the glass analyses. So right now, I'm still looking for more morb. because I want to define this further. We actually have acquired some more morb. We'll be working on it soon. Excuse me. But right now, we showed that basically this method works for more primitive lavas, which similar to the komatiites we worked on and to the more primitive morb. But for more evolved lavas, it's rather suspect. And this is likely due to the glass olivine disequilibrium. For the data we have that are high MgO, there's only 4 of them. There's no distinction of morb with volatile concentrations or isotopic composition. It's been shown before by Cottrell et al. 2013 that isotopically enriched morbs are more reduced. We don't see that in our data set, though we do have larger air bars. And we just need more morbs to define this. So basically what we've shown in this paper, this came out rather recently, is that vanadium and olivine and iron Zane's oxybarometry gives similar results in primitive morb, but in more evolved morb, vanadium and olivine oxybarometry doesn't really work. Then we'll move on to part 3. How am I on time? I'm doing okay. Where we'll continue to talk about modern day lavas. We'll talk about modern day plume lavas. We talked about modern day morb lavas, and we'll look at present day mantle redox heterogeneity. So we looked at temporal heterogeneity, varying with time with komatiites, and now we'll look at spatial heterogeneity, varying with place in lavas that erupted around the same time. So many of you know this, but I'm going to run through it real quick anyway, because this is from Xi-Chun Huang and other people. Yeah, most of these are Huang that said that. So there's a variety of isotopic M members are found in mantle-derived lavas. Pretty much all of the morb is found at this one M member, DMM. DMM is down here, it's down here. So morb, despite being the vast majority of oceanic lavas erupted, shows isotopic signatures that are relatively homogeneous and that are a small fraction of the range shown in oceanic lavas. Plume lavas show a variety of isotopic signatures, including high mu, which is radiogenic lead, but not very sort of radiogenic neodymium, strontium, hafnium, other things. And this is thought to be the result of the recycling of oxidized oceanic crust. We have EM2, enriched mantle 2, which is the result of recycling of terrigenous sediments, and EM1, which is the result of probably recycling pelagic sediments, though EM1's a little more debated about what it is. And this is shown in a wide variety of isotope systems. This is neodymium and lead. This is osmium and lead, and we lead to different sort of N members here. This is helium and lead. Helium is kind of decoupled from other isotopic systems, where we'll get really undegassed signatures, like very high helium 3-4. Helium 3 is primordial, helium 4 is formed by radiogenic decay. So high 3-4 indicates that the mantle source of the lava hasn't sort of interacted with the atmosphere really at all. And you'll notice things with more radiogenic lead have low helium ratios. This is largely due to the fact that they sample recycled oceanic crust, which has interacted with the atmosphere. So we have a wide variety of isotopic signatures, likely resulting from recycled lithologies, different types of sediments, oxidized oceanic crust. So what we thought to ask with this is a whole series of papers is to see, can plume lavas also show surficial redox signatures? They show surficial isotopic signatures. So we know that altered oceanic crust is very oxidized. It has an iron plus 3 over total iron, anywhere from 30% to 50% due to interaction with the atmosphere, serpentinization. And the mantle is anywhere from 2 to 3%. So 30 to 50% versus 2 to 3%. So you're pumping this oxidized material down into the mantle. And then we think it's coming back up in plume lavas. So we think those plume lavas should show higher concentrations of oxidants and thus higher oxygen fugacity. It's notable that you don't need deep ocean oxygenation to oxidize AOC. You just need serpentinization. So some plumes I've thought to contain large amounts of recycled AOCs, such as high mu flavored islands, i.e. Mangaya, St. Helena. They should show oxidized signatures, we kind of did a back of the envelope mass balance before undertaking this. It's around 20% oxidized oceanic crust and 80% ambient mantle will yield basalts around 1.3 log units more oxidized than Morb, assuming that the only difference between these two end members is the iron plus 3 over total iron. That's easily detectable. Terrigenous sediments, i.e. EM2, are likely very volumetrically minor, even in extreme EM2 lavas. The most extreme EM2 have less than 7%. And they're very iron poor, they're very oxidant poor, so they don't really have a measurable effect on Plume FO2 from our calculations. Pelagic sediments are more interesting. They're also volumetrically minor, like less than 5%, even in extreme EM1 lavas. But if they were highly organic rich, they could have a strong reducing effect on the mantle. But it's unclear if organic carbon makes it into the deep mantle, if it makes it through subduction zones. But it's known that things with lavas that have interacted with large amounts of pelagic sediments, we've seen this at the surface, will become very, very reduced to the point where they crystallize metal. This is shown in a few places on Earth. So if we are getting black shales into the source of ocean island basalts, that would lead to very high amounts of reduction. Come on. Let's go. There we go. Okay. So there's been a couple of studies before we started in this where we look at Plume FO2. So they mainly looked at melt inclusions and used iron zanes. We just talked about zanes. This is from Musalam et al., 2019. This is from Fogo, the Cape Verde hotspot, Lanzarote, El Hierro, which are in the Canary Islands, Kilauea, Mauna Kea, those are in Hawaii. Laki is in Iceland, and then the Erebus hotspot, which is in Antarctica. What they showed overall was a strong influence of degassing. So you'll notice these are some of the most sulfur-rich lavas on Earth. These have like 5,000 ppm sulfur. These are very sulfur-rich. But as we degas sulfur, we get overall more reduced by over 2 log units. However, they basically regressed sulfur versus FO2 and to what they thought the sulfur content of the parental magmas were, and said, oh, plume lavas are oxidized. They're around plus 2.5, 2 to 2.5 delta F from Q. They're more oxidized than Morb, significantly. However, no prior studies than us correlated FO2 with isotopic data to try to sort of look at mantle end members to see if they have different oxygen fugacity. And to do this, we determined the oxygen fugacity of 6 OIB suites with diverse isotopic signatures. We did it with vanadium and olivine oxybarometry because that's what I do, and we don't do zanes. So we did entirely vanadium and olivine oxybarometry. So this is what we get. This is several thousand data. This is all me. It's the Morb data. You'll notice we need more Morb data. This is various places in Iceland, the Western Rift Zone, the Eastern Rift Zone, Northern Rift Zone, tertiary lavas from Iceland. Each spot is a single olivine analysis. We see reunion and we see the other OIBs. We see literature data from Iceland. Iceland's the only OIB in which we had some literature data. And we see olivine MgO content versus olivine vanadium content. You'll notice that there is some overlap, but Morb ranges to much higher vanadium contents for, oh dear, for a given olivine Mg number than OIB does. This is largely because of its more reduced signatures. OIB, lower vanadium content at a given Mg number, largely because it's more oxidized. So this is kind of our big money figure that we see here. Here's the Iceland data, Iceland literature. There's other OIB data. The other OIB data are from the Azores. They're from Samoa, they're from Canary, and they're from Mangaia, which is in the Cook Islands and sort of the type locality for high mu, for radiogenic lead. So we found a couple things. We found oxygen fugacity that ranged up as high as postulated by Musalam, plus 2.5, almost to plus 3 in terms of oxygen fugacity. Very oxidized lavas. Mind you, Morb is right around 0. So some of these are significantly more oxidized. However, we found some correlations. The slope is resolved from 0. Even this is a 95% confidence interval. even when considering the air bars. We found that with the parental magma MgO content, which we calculated in each case, that lower parental magma MgO contents are more oxidized and higher parental magma MgO contents are more reduced. We also see some correlation with some other geochemical parameters. We see with lanthanum over ytterbium, normalized to chondrites, we see an even better correlation. And what we see, and this is a proxy for both enrichment of a mantle source and degree of partial melting. We see a strong positive correlation. Lower degrees of partial melting, more enriched sources are more oxidized. We show less good correlations with isotopic signatures, but they are still resolved from zero. They're still statistically significant. With lead, we're more radiogenic in lead, i.e. more altered oceanic crust in their sources are more oxidized. This is Mangaia. These are the most radiogenic lead oceanic lavas on Earth. And we see a less good correlation with neodymium, but it's still statistically significant, where things that are more unradiogenic and neodymium, i.e. more enriched, are overall more oxidized than things that are more radiogenic and neodymium and more depleted are more reduced. Osmium, we don't see a great correlation, but there is sort of a hint of one, that things that are more radiogenic in osmium are overall more oxidized, but this kind of depends on this blob of data from Iceland down there. And the one in which we find no statistically significant correlation, there's no real correlation here, is with helium. So we tested some of the most undegassed lavas on Earth. This is a tertiary lava from Iceland. It's a helium-3 over helium-4 ratio of around 35. The highest on Earth is around 62, but around anything above 30 is considered incredibly rare and sort of very high. We see no correlation with FO2. So we see a couple things. I just pointed out all the correlations we see. We see no real correlation with osmium or helium. We see some with lead and neodymium. We see rather strong ones with parental magma FO2. Okay, sorry about that. And with bulk rock, lanthanum, ytterbium. So one thing that we tested is we know that fractional crystallization of iron +2 rich minerals, i.e. olivine. Olivine is an iron +2 rich mineral. It has no iron +3 in it, can oxidize and melt. So we did some modeling, and this is what we found, is essentially if we oxidize lots and lots of olivine, this is the slope we get in FMQ versus MgO space. And this slope doesn't explain our data trend. It's too shallow. So fractional crystallization does oxidize a lava, but the effect is relatively small and can't explain our most oxidized samples. So degassing and crustal contamination, degassing can lead to strong reduction. However, we don't think we would see a single correlation, and there's no reason it would be correlated with isotopes or with lanthanum over ytterbium ratio with degassing to lead to a similar correlation. Same with crustal contamination. For 6 global plume localities, all of which erupted on oceanic crust, we're unlikely to see a single crustal contamination trend, so we can discount both of these, leading to our correlations. We also did some modeling. We looked at differential partial melting of a homogeneous mantle peridotite. It's unable to explain the correlations. Essentially, you do get slightly more oxidized lavas when you melt a homogeneous mantle peridotite at lower degrees of melting, because iron +3 is slightly more incompatible than iron +2. However, this effect is way too small to lead to the correlation we've shown. And so what we basically came up with in the end is that correlations between parental magma MgO and FO2 and degree of melting, i.e., and isotopic enrichment, it reflects preferential melting of oxidized enriched fusible lithologies at low melt fraction. What I mean by this is here we have very low melt fraction in these oxidized lavas. That's why they're high MgO. That's why they're high lanthanum ytterbium. And therefore, we're only melting sort of little pockets of the mantle. Maybe they're peroxenite, maybe they're more fusible peridotite of the mantle that are more oxidized, leading to these lavas. While down here, we're diluting those more oxidized bits of the mantle with just ambient depleted upper mantle. And so this is my last bit, were conclusions. We know oxidants are mainly hosted by recycling associated lithologies, either eclogites, peroxenites, peridotites, which we know to exist in the mantle. And that such lithologies have enriched isotopes. They melt early, so at low melt fraction. They get oxidized melts at low melt fraction. And what we know from this is that our isotopic M members, high mu, EM1, EM2, are unresolvable from each other in FO2. We need more samples. We have very high mu samples, but EM1 and EM2, we don't have enough samples. We know that the depleted M member of MORB, of OIB, approaches MORB FO2. And whether they're the same, whether the depleted M member of OIBs and ambient MORB mantle are the same thing, is debated by geochemists. We know there's no relationship with helium isotopes. So what we can say is, at least in the modern mantle, the lower mantle not significantly more oxidized than the upper mantle. It's hard to get M members right now because we don't have iron concentrations of N members. And what I can say is this kind of highlights what I said with the chromatites, is that whole Earth redox cycling, it occurs on a 200 million year time scale, which is how long it takes for crust to subduct to the core mantle boundary and come back up in a plume. And this may modulate atmospheric chemistry on long time scales, and therefore we get more evidence for mantle redox coupled to atmospheric redox. This is a whole bunch of papers. Questions. And here's my favorite figure in the world, again. But thank you.
Okay, thank you. And now it's time for questions from our participants. So feel free to open your mic to ask a question, or you could leave your question in the chat and I could ask a question on your behalf. So questions, please.
Hi, Robert. I have a question.
Yes.
Could you please move your slide to the chromatite part?
Yeah, I'm going back. Give me a second.
Thank you.
My computer's not very responsive today. Chromatites.
To the oxidizing trend of the mantle, that diagram.
Yeah.
Okay.
Okay. We'll catch up. We'll get there. Give me a second.
Okay.
Yeah.
Thank you. Yeah, this one. So my question is, even at present, the crustal material is more oxidized than the mantle, right? The iron 3+ ratio is higher in the crustal material than the mantle. But what if subduction, recycling of the crustal material is the reason, or partly the reason, causing the oxidization of the mantle? Why the oxidization stopped at around 1.9 billion years ago? Yeah, that's my question.
That's a good question. That's actually one of the main problems we had with this theory. Basically, that's kind of my main problem with the recycling of oceanic crust and why I don't think this model will work. Because like you said, we continue to recycle oceanic crust. It's still more oxidized than the mantle. So this does not really work, because why would our oxidation trend stop? So therefore, why I think our trend stopped is that we're just getting a well-mixed mantle. We're getting a mantle that is well-mixed. And so that this theory, whole mantle mixing, is what leads to our oxidation trend, and that it's unrelated to recycling of oceanic crust. But yeah, good question. Because otherwise you would think it would continue forever.
Yeah, I agree. Thank you. I probably missed this part. Thank you very much.
Yeah, of course.
The next question, please.
Oh, hi, Rob. Can I have a question?
Mm-hmm.
So,
Yeah, go ahead.
So I have two questions. The first one is, can you introduce briefly about the effect of degassing on the oxygen fugacity of the magmas? So is it reducing or oxidizing the magma?
Yeah, I'll show you. So yeah, so this is a figure from Musalam, but basically what we see, there's never been evidence in a mantle-derived magma that it would ever oxidize. So what's only ever been shown is that sulfur degassing leads to reduction in a magma. And so why that is that we have sulfur in most mantle-derived magmas is S-2. It's dissolved as sulfide. And then it degasses as SO2, sulfur dioxide. And therefore, it needs to become oxidized. So it reacts with iron +3 in its parental magma and reduces that iron +3 to iron +2. So as we lose sulfur, we also lose iron +3, leading to this reduction trend. It's never been shown that it oxidizes.
Okay, so
it theoretically could, but it's never been shown in a natural magma.
Okay, so like it is impossible to oxidize the magma, because if you have, so I'm thinking that if you have a lot of sulfates in the magma and in oxidized magma, and if the sulfate degassing degassing as to the SO2, then it is possible to oxidize the magma. Right? But like in the nature samples, you don't see any signal for oxidizing the magmas, right?
Yeah. Now, people have talked about that, especially in very sort of oxidized arc magmas. I'd really like to get a hold of some of those and being able to measure iron valence and amount of sulfur, because I think you would see that. I think you would see oxidation if you saw a magma that was so oxidized that you had sulfate dissolved in the liquid. But unfortunately, that hasn't been shown yet. I think it exists, but it hasn't been shown yet.
Okay. So my second question is that about the oxygen fugacity of your commodities. So can you go back to the commodity part?
Yes.
So can you evaluate the effect of the temperature on the oxygen fugacity? Because people think that if you have temperature effect, can the decreasing of temperature affect what you have calculated for the oxygen fugacity?
Yeah. So basically, temperature, there's two ways that temperature can affect it. The first one is that temperature can affect the partition coefficient and therefore lead to us get erroneous oxygen fugacity that's already been parameterized. The temperature is right here. We get liquidus temperatures for each of our komatiite flows and each of our OIBs from their parental magma MgO contents. We account for that. And the other thing you said is that temperature can actually change the oxygen fugacity of a mantle source as it changes. And basically, we looked at that in our 2019 paper. I don't remember the specifics. We did some modeling. One of the reviewers asked that same question, but you should look at that 2019 paper. It doesn't cause a very large effect. It's like less than half a log unit with the amount of change, with the amount of temperature change we would see in our lavas. Basically, because some of the modern lavas, i.e. the Gorgona ones, which are 90 million years, which are right here, are similar in temperature to a lot of the Archean lavas. So the change in temperature from Archean to modern day was not that big, at least for our sample set, and it doesn't affect the oxygen fugacity very much. But you can go look at that modeling that exists.
Okay, thank you.
Mm-hmm.
Okay, next question, please. Then I have two questions. I think they're short ones. So the first one is, you don't need to go to that slides, but I think in one of your slides before the end of the talk, it shows the fractional crystallization. But they consider that it could affect a redox. You show that it only showed a little bit. So how much? What's the maximum amount of olivine that you add to the system?
To the system to correct. It's around,
for correct.
It can be anywhere from 30 to 40%, but we found no correlation between the amount of olivine added and the FO2. So we don't see any real, we showed that in the komatiite paper. We don't see any correlation between that. It can vary between anywhere from like 30 to 40%. Some of the OIBs are almost entirely lava compositions. Like there are ones that are less than 1% olivine added. Like the bulk rock is in equilibrium with its olivine. And therefore, but yes, anywhere kind of gets up to 40%.
Okay.
Added or subtracted. It's often subtracted because we're looking at cumulates, because we choose lavas that are very rich in olivine because they're easy to laser. So
Okay. Thank you. And the last question is your favorite cartoon from the Lecomte. So
yeah,
you drew that primordial one. Although in your talk, I think you would like to say that the lower mantle has the same oxygen fugacity as the upper mantle, according to the helium, according to the redox of the samples with the abnormal helium anomalies. Yeah, but if you don't take that like evidence, or like I said, do you interpret that the primordial ones are more oxidized or more reduced than
I don't know.
demanded from early until now? I don't know. I think it's an open question, but I would like to see what's your perspective on that.
I would think in the early Earth it would be more oxidized because of that iron disproportionation with bridgemanite. However, as you're probably aware if you work in mantle geochemistry, we live in an era where 182 tungsten is found in everything. And that's a primordial signature. Every plume erupts 182 tungsten anomalies, and those must have formed in some primordial process very, very early in the Earth. I don't think it has a different oxygen fugacity, though I am sort of on the hunt right now for lavas that have 182 tungsten anomalies to do FO2 in, which I think would be one of the best ways to look to see if the primordial mantle is different. As you said, the helium doesn't really show anything. However, I hope no one here is a noble gas geochemist, because I think sometimes helium, we're not getting what we're getting. You know, I feel like a lot of plumes, you don't see good correlations between noble gas signatures and with like lithophile element signatures, because the degassing messes everything up. So sometimes we might not see a correlation because like some of our other lavas could have had high helium 3-4, but then lost all their helium, or we don't have data, or helium's hard. So I'm going to try to use 182 tungsten, but I'm always looking for more samples that are just sort of high olivine mantle derived lavas, and I laser them for free. We have free laser work here, so if anyone wants to send me some olivine rich mantle derived lavas, I would love them.
Okay. Okay, thank you very much, Robert Willie, and thanks everyone for your participation. So could you stop sharing? And then before we turn the video off, meeting off in about 30 seconds to 1 minute. So could everyone open your video if you can and show your smiling faces to our speaker today to show appreciation.